All right, next problem. 5 kilogram block starts at a speed of 10 meters per second, right here, at the top of a roller coaster, shown above. What is the kinetic energy at the top? Okay, that's easy enough. That's just a plug in. Ke equals 1 half mv squared equals 1 half. It's 5.0 kg times the velocity is 10 meters per second, but that gets squared in the equation. So it's the 100 times that's 500 is 250 joules. Yeah, that's easy enough. Okay. So now it's got kinetic, but you know what? Up here, recognize it's moving. It's got kinetic. Let's write this in of 250 joules. It's always good to put information right into your picture. You know what else I'm going to do? 'Cause since this is an energy problem, 5 plus 2, this is 10 meters high. So it's mgh, 10 meters high. Whoops. 5 kilograms. 5 kg really should be 5.0 times 10 meters per second squared times a height of 10 meters. It's got a potential energy of 500 joules at the top, right there. So it's got two energies, potential and kinetic. What is the gravity? Well, here it is, gravitational potential energy. We did that at the top relative to the ground. PE is m GH, which is 5.0 kg. You've seen it already, 10 meters per second squared. And the height, 5 plus 2 plus 3, is 10 meters. It is 500 joules, 500 joules, or if you like, Newton times meters, because that's what a joule is, a Newton times meter. What is the block's total energy at the top? Well, that's simple. Simple. It has only two energies. It has kinetic. It has potential. 750 joules is its total energy. Um, None of this is the new stuff because there's no mention of any work done. In fact, just to give you an overview, this object will go down. It'll go down the ramp and go through this, not ramp, but through this roller coaster. Do a loop de loop, swing a circle, and come back. And this is the only point where it's going to get some work done on it. And you're going to see that it actually stops right here. And all this friction does work to stop it. So just to show you what's coming up next. Um, if it has, let's say it has 1,000 joules before it hits there's no friction on the roller coaster till right here. So if it has 1,000 joules right before it hits friction and it's going to stop, what's the work? 1,000 joules of kinetic energy. How much work do you have to do, stop a car going 1,000 joules? You have to do 1,000 joules of work if it truly stops, because that's the change in kinetic energy. So that's where we're going. So same roller coaster, different questions and more difficult questions. If the track is completely frictionless, I told you that, and there's no air resistance, we don't have to worry about that kind of work. It won't lose any energy until it reaches the bottom where it hits that rough patch where the coefficient's zero point 0.5. And friction, of course, takes away the energy, actually turns it into heat energy. That's where the kinetic energy will go, but we'll talk about that later. What is the GPE, gravitational potential energy at point A? Well, we've done the gravitational potential energy at point A already. Let's go over here. It is the gravitational potential energy is 500 joules. We found that out already. Find the gravitation. I think that's what. Yeah, my bad. No, we didn't find it. It's actually over here. What's the gravitational potential energy at A? Well, it's just mgh. M times g, still it's a 5 kilogram block. Do you remember that? 5.0 kg block. So it's 5 times 10 is 50 newtons times the height is given right here is 5 meters. So it's 250 joules is the PE. mg, 5 times 10 is 250. Alrighty. Okay. And then calculate the block's total energy. Um, then calculate how much the block's total energy must be in the form of Ke. Well, we found the total energy is 750. So if it's got that much PE, this is a little sloppy. Let me make it better. The PE is 250 joules. Then what must the Ke be? Well, if there's no work against friction in this roller coaster, it must be 500 joules. Why? Because the total energy, when there's no work done on or by my system, doesn't change. It was 750 before when it was at the top. It should still be 750. So this must be 500 joules. All right. Find the speed at point A. Okay. That's easy enough. That's the KE. It's 1/2 mv squared, 1/2 of 5.0 kg times v squared. So equals the 500 we found just before. You can see I have answers over here. 500. So the velocity, when you do this work here, I would multiply both sides by 2, divide by, clear this out, divide by 5. Multiplying by 2 is 1,000. Divided by 5 is 100. Well, yeah, 1,000. No, 1,000 divided by 5 is what, 200, isn't it? So the velocity at point A, which is right here. Let me see. I've got the work done over here. The velocity at point A is when you round it, it's to two significant digits. It's 13 meters per second. Repeat the same thing for B, C, and D. Okay, B. I got to find the new PE, which is mg 5 times 10, mg 50 newtons, times the h, which is 7 meters. One's really should probably be 7.0, but okay, 350 joules. Yeah, imagine these are all 3.0, 2.0, and 5.0. So 350. So the total has to be what's the KE? Well, we've established that the total energy was 750. So it's got to always be 750 because this is frictionless, no air friction, no friction on the ramp. It's always got to be 750. So there you go. That's 400. Good. Just check that I got the right answer. Terrific. And now what's the velocity? Well, KE is 1/2 mv squared. So m is 5, and so you could do the math, right? Oops. Why isn't that not showing? Here we go. 5.0, let's pick it. 5.0 kg. And the math is pretty simple here, isn't it? And v squared. And now it's just 400 equals 1/2 mv squared. I'm going to clear the 1/2. I'll multiply both sides by 2. Get 800 is 5v squared. Divide both sides by 5. And then take the square root. And what you get at B, yes, at B is, wait a second. I think I made a mistake here. Hold on. I gave you the wrong answer for A. Yeah, I did give you sorry about that. I had the answer key, but I looked the wrong place. If you do the work on this, you get 14 meters per second when you do this work. So I just gave the wrong answer. This actually is 13, which makes sense that it's slower because it's higher up. It's it's going to, some of that KE will turn to PE up here. So sorry about that. This is actually 14. That's double check when you round it, it's 14. You do the math. I'm sure you probably found that out when you did the math yourself. That's 13. Now you have to do it at D. This is a lot of work, isn't it? So this PE. At D, it has new PE. Now, you told the radius is 1.5. That means that this is 3, right? 1.5, 1.5, so it's 3. So it's 50. mg is 50 times h is 3. So it's 150 joules. So it's the same process again and again. This is 3 meters. I don't know. And so if the PE is 150, then the KE is 600 joules because they all have to add up to 750 because that's what we got before. The total before is 750. I don't think I'm going to, I don't think I can start you out, but you can do the work. Equals, of course, 1/2 mv squared. And this is just a simple math problem to find the v. Do I even have it worked out? No, I don't, because I think it's kind of silly to keep doing simple geometry problems. You could certainly work that out. That would be 1/2 of 5 times v squared. You would just, the solution is pretty simple. I'm going to give you the, now let's go down to, that was D. I skipped C. The PE here is 0 joules. So it's all KE at the bottom, which is 750 joules. And once again, I could find the velocity, but I think it's very repetitive. It's just 1/2 of 5 times v squared. You can work that out. It's silly to take the time to do that. Now, so the kinetic energy is 750 here. So let's go where it starts to get interesting. So after it leaves the loop-de-loop, this is like a loop-de-loop in a roller coaster. How much energy does the block have as it exits the loop-de-loop? Well, we've already done that. PE, it's at the bottom, so it has no height. It is all kinetic. All right. How much? Oh, that's actually goes over here because that's the question. How much total energy does the block have as it exits the loop-de-loop? At the bottom, the height equals 0 at the bottom. Here's where it exits the loop-de-loop, right there. Here, no height. And how large is how much energy does the friction take away? If it's going to, we're told that it stops it, it must take away this much energy. All right, right? Because how much energy do you have to take away from something that has an energy of 750 joules? How large is the frictional force? Well, work. What was the work to stop? The work of friction equals the friction force times the distance it acts is equal to that. Well, it's going to be equal the change of the KE, which I have to make negative because it's going to reduce it to 0. It's going to go from 750 to 0. That's a negative change. So the friction, now the distance up here, the friction axis, let's see the distance it acts. Actually, what's interesting is we don't see the distance. Hmm. Okay. That's interesting. What's the frictional force acting on the object? Wow, that's interesting. You don't know the distance over here. Oftentimes you do. Well, you see that delta S is question mark. Okay. All right. We can work on this. So the uh the friction equals mu times normal. It's a flat surface, so it's Fg times D equals negative 750 joules. So the mu, so this is just the friction, mu times Fg. So the mu is 0.5. The coefficient's 0.5, so 0.50, make 0.50, times the weight is 50 newtons because it was 5 kilograms, times the D is unknown, equals negative 750 joules. So, actually, wait a second. I actually have the friction. What am I doing here? What's the frictional force? That is mu times Fg. So what am I doing here? Friction equals 0.50 times the 50 newtons. That's the weight because it was 5 kilograms. So the friction is, yeah, there it is right there, negative 25. It acts in opposite direction of what we call positive to the right. So what am I doing here? Did all this nonsense was this will come later. I've kind of jumped ahead. So let's go so I don't mess you up here. How do you find the friction? Friction equals mu times normal. It's a flat surface, so the normal is the weight force. See? And let me get rid of this nonsense over here. Got messed up. Sorry. I kind of got ahead of the game here. This will come later. So friction is mu times normal. And here we go. Goes like that. And yeah, 25 mu times normal. 0.5 times 50. Because remember that it's 5 kilograms. So 5 times 10 is 50. Now here's where we go with how long does the block slide before stopping? So you can see now I got ahead of myself here. So the work done against friction is equal to the change in kinetic energy. Work done against friction is friction times D equals the change in kinetic energy. If the block has a kinetic energy of 750 and it's stopped, then it's a negative 750 change. The work done on my block changed the energy of my block. So negative 25 newtons times D equals negative 750. And you can see the answer is 30 meters. Because you divide both sides by negative 50 and you get you get 30. And that's it for this worksheet.